Today we have the pleasure of having Professor Alakabha Datta from the University of Mississippi. Alakabha got his PhD from the University of Hawaii with Sandy Maskata. He later got his did a postdoc in Iowa State University, and University of Montreal, and University of Toronto. He worked on a variety of topics of PSM physics, but today he's going to talk about something that falls under what he has over 20 years of expertise, which is flavor physics.
Okay, thank you. Thank you for having me here. I just want to talk about some new results that that kind of got us excited the last few years. And please feel free to ask questions. I just want it to be an informal kind of seminar. And the reason why I have 60 slides is, when you go to a talk, you decide, okay, I'm going to focus on this part. The last time I gave this talk, I decided, I'm not going to talk about these things. And when I went to the talk, all the questions were about those areas. So I've got everything, so, I don't know. So we're not going to go through all this stuff. But so in recent times, there are the anomalies in the decays. And it's interesting because it indicates new physics, but it's lepton non-universal. So the physics is different for the different generations. And so they're in two areas. What is in semi-electronic? So the decays are very simple. So this is a tree-level semi-electronic decay. It's a charge current transition, and it's called. We're going to use this what's called the RD star bundle. And they're also the semi-electronic neutral current, which is B to S N plus N minus. And these are known as the RK and RK star. But even before, so these all measurements are showing deviations from the standard model, and it's the kind of new physics that you need is lepton non-universal. So it's different for different generations of leptons. But even before that, there were some measurements. If you just look at the LSCB does a lot of measurements in B2S, mu plus, mu minus modes, and they were finding some deviations. And we'll talk about what's called the P5, and also the Bragg ratios were less. And then last year, there was a flurry of activity. In May, there was another measurement of what is the RK star, and it went in the same direction as RK. And so there were kind of large papers. So there's been a lot of work on this, and I'll just kind of first give a review of what the RT star puzzle is, what are the theoretical predictions, how solid they are, and there are a lot of measurements that are planned in the future, and we can learn a lot about this puzzle from future measurements and talk about those measurements. Then I will talk about the B2S, what's called the neutral current RK star puzzles, and then we're going to look at there are variety of things that you can do. You can kind of look at other decays, non-electronic decays, which are also similar to this. Neutral current, but we'll see, maybe I'll kind of skip this. But what I'll consider is that this idea that we propose that there might be a simultaneous explanation of these two puzzles and how you can test them. And finally, something that we did recently was, maybe these neutral current anomalies can proceed through new physics where the mediator is light. So that's something of interest. Here. So what is the RT star puzzle? And so if you have not heard about this before, it's just a semi-electronic decay. So you have got a B goes into a C, so you have a B meson which goes into a D meson. In the standard model, emits a W, and it produces atomic income. Right? And so what we do, the amplitude is very simple. We have a B to D, and then there is this hydronic current, and then there is this electronic current here. And you consider the ratios of B to D going to tau to L, where L is the electron or the muon, and you take the ratios. And the reason for taking the ratio is a lot of unknown quantities cancel. For instance, the BCD would cancel in the ratio. A lot of the hadronic form factor effects also cancel. A lot of the systematic effects cancel. And in the standard model, you know that the W couples equally to all the generation of the leptons, the electron, muon, and so it should be 1. But of course, the tau is heavier than the muon and the electron. But it's not 1, but it's something that we can calculate very precisely. And so if you're seeing a deviation here, you're looking at new physics which couples differently to the different generation systems. So you can look at this and you can write down many new physics models, and I'm not going to talk. There are many. I'm not going to talk about that. So the obvious thing that received a lot of attention before was if you had a charge stick, so instead of a W minus, in many extensions, you can have a charge stick like the similar model. You can have a W prime. And the other situation is you could have a B, and instead of turning into a C, you can turn it into a lepton. So B goes to this like a tau, and instead of a tau, you have a charm. So in that case, the exchange particle would be a leptoquark. So those are also models that people have discussed. And the other option is instead of a tau, suppose the tau mixes with some terrain neutrinos, then you can have an additional. So these are the kind of general classes of models that people have kind of discussed in this. So what is the puzzle here? So here are the measurements. So these have been measured by all the experiment, the LHCb, the Bell-2, the Bobard. And if you take the average of all this, you come with these values. And there are very good standard model predictions for this, because there is a whole technology of heavy quark symmetry that have been used to study these form factors for a very long time, since the 1990s. And now the experiments there are enough data that you can actually measure these form factors. So, there are these form factors here written in terms of some parameter. You go do an experiment and you can actually measure this. And so the predictions are very very well understood, small errors. And not only that, there are now lattice calculations of this. And if you look at this, if you look at what is called the phenomenological approach, that you have some form factors, you parameterize them in terms of some parameters that you go and measure from experiments, and then there is this lattice, and you see the agreement is great. So we are.
So you also have lattice for RT star?
Not yet.
Not yet.
Not yet. But for RT star, you have to still use the phenomenological. And then there are various groups that have actually looked at this. So the problem is not here. I mean, the problem could be somewhere. I mean, if this kind of effect goes away, it's probably due to experiment. I mean, so these numbers are going to come close to this. It's not that these numbers are going to go there. Because I think we understand the theory very well. So there are kind of various things, and as I said, you can kind of look at all kinds of models, and the one thing that the reason I want to point out is that you can do a model independent approach to new physics. You can just kind of write down all the operators here. And the one that I want to focus on is the one that's going to be an important part for this talk. Is this very simple and kind of boring operator which just modifies. So this is the standard model piece, and you're just adding one, the piece of L. And then you can have the right-handed, you can have, so depending on your model, so if you had a model with leptoquarks, you would generally produce tensor currents and scalar currents. If you have charged Higgs, then you're going to produce kind of the scalar operators, and so on. So this is the way. And in principle, you can actually, the way to do it is you can actually measure all of this coupling. So there is going to be enough data that you could actually measure this. So what you actually do is, and we'll talk about this, so as an example, you can look at the full decay distribution. So you have a B which goes into a D star, and that D star decays into D pi, and then in the standard model you have an offshot W which goes into a lepton, and they are at these angles, and you can actually construct this full angular distribution. And these angular distributions are written in terms of what we call the helicity amplitudes, and they contain the couplings here, the new physics couplings and the form factors. And so we kind of understand all these form factors well. And in principle, from the angular distribution, you could extract all of this helicity amplitudes and actually measure all these kind of couplings. So there are kind of a lot of things, and I don't want to kind of go into details. One of the things that you could measure is what are called CP violating quantities, which are called triple products. And those are, again, very clean signals of in physics, so you would actually check if there are phases in this helicity amplitude. If you look at the helicity amplitudes, the only weak phase that appears is in the BCB here, right? And there is only one. And so if you go and compute things like this, the BCB kind of cancels, and this is 0 in the standard model. So if there's new amplitude and new phases, you can actually look at it. Okay, so there is also what is called inclusive decays, and so that's also a future measurement that can be made. And here, instead of looking at particular exclusive states like D and D star, you sum over all the states, and these are even better than the exclusive states because there are no form factors here, and the heavy quark expansion is very well developed here, and you can make a kind of prediction here. In fact, there was a 2001 result from lab, which is not really a measurement, a clear measurement of the inclusive. So what they observe is they have Z going to be V bar, and then V goes into any X, and then the tau nu. So it's not really, now the B goes and forms all kinds of hadrons, it forms B mesons, lambda B's, and everything. So it's kind of an average of this. But you know, you can have a sense of what this kind of measurement is, and you know you can get some constraints, and so already from the lab measurements. So, okay, so and there are the underlying transition is B to C, so you can kind of look at all of the processes. For instance, you can look at the B's of C, and there are already measurements which kind of constrain this, and there's going to be a new measurement coming from LHC B soon, which will be lambda B instead of the B, and these measurements are also going to put a lot of constraints. So you know, these are kind of possible constraints.
The operator structure could be different.
Yeah. So because the operator has different effects on this decay, so you get a lot. So this, I don't want to kind of go into details, but so that's kind of what is happening. What I want to kind of mention here is that if you look at the data, and the data has changed a little bit here now. So this ratio, what we consider is the ratio is RD over RT standard model. It's the same, roughly. I mean, it used to be even closer. Right? It used to be like 1.30 and 1.25, and that's when we wrote the paper. And it seems that this, what is interesting here is this ratio is the same. This has got large error, it's consistent. And this is exactly what you would predict if there is a new physics which only changes the standard model. So if you go back and look at here, so this is a piece which only affects the left-handed. So you've got new physics which only affects the left-handed fields, right? So if you get a left-handed field, then it's just a scaling of the standard model piece, and you predict this ratio to be the same. And so you have got some new physics which only affect the left-handed fields, right? And it's also consistent with some of the distributions. The distributions are just getting to be measured, but there is a measurement of the d gamma dq square which has the same shape as the standard model. So this is an idea which suggests that the new physics is also B minus A.
So what about the scalar operators? You did not, so they can also do the same thing, right? Like
No, the scalar will not do this. You will have different predictions.
You have different predictions?
Yeah, and the shape will be also.
So this is the best fit. Like
This is the best fit. Yeah, only that. So let's go back. So this was the RD. Let's go back to the other anomaly, which is neutral current, right? And in the standard model, it's something where you would expect new physics because it goes through penguin, and the penguin processes in the standard model are small, and it goes through this kind of penguin here. And if you follow this, you will hear a lot about these two operators, C9 and C10. So those are the electric penguin here. You have to worry about the B2S nu bar, which there is a strong constraint coming from there, and of course the usual B2S gamma. So here the gamma can, kind of, you can have an off-shell gamma which produces N plus N minus, and so you get contribution from C9, C10, and C7. Okay. Now so what are the so in the standard model it's again mostly left-handed. So if you look at So even though here it's not, so C9 is roughly equal to minus C10. So again, it's mostly B minus A. And you see that C9 and C10 dominates because C7 is small, it's about a factor of 10 less than C9 and C10. So most of this goes through this. And we look at what is called the low Q-square region, and we'll say why. This is the region where things are clean, and we'll talk a little bit about this later on in the slide. But if you go to very low Q squared, then the photon pole is going to dominate. So because you can now have the gamma, and the gamma, when a gamma goes and splits into a photon, there is a 1 over Q squared, which is coming from the photon propagator. So at very low Q square region, the C7 term becomes important. And of course, the main problem is that, this B to S L plus L minus actually come from B going to, say, S and J psi, so non-leptonically, and then J psi goes to L plus L minus. And so you have to get rid of this resonance region. So that's the main problem that you have to deal with. So the resonance region is cut off, so we go to the low Q square region where things are nice and clean. So for some time, people, LHCb made a lot of measurement in K star and B minus, and they found that there were some deviations from the standard model. They found that the branching ratios were lower than the standard model predictions. And there was this angular variable P5, which was also lower. Okay. But then you can ask that, how clean are these predictions? This is all hydronic stuff, and I, for one, didn't pay much attention to this. But let's talk about, just like we had for the B to D star, so we do an angular analysis here. So you have got a B, which decays into K star and goes into K pi, and then there is, you can have the Z, which goes into plus B minus, and you have all these angles. And what you do is you write down this whole angular distribution, and the experiments have actually constructed this, and they have measured all these quantities. So these are all the angular quantities that you can measure, and one of the quantity which is kind of very interesting is what is called the P5, and the reason why it's interesting is because a lot of the hadronic stuff, form factors and everything cancel in this ratio, at least to Liddy model, right? So if you're in the small Q square region, then the P5 is a very clean observable, clean test standard model. And so what they find is, so here is the P5, and in this bin of Q squared from 1 to 6, there's this is the standard model prediction, this is the LHCb, I think the CMS and Atlas. So this is the main kind of deviation that you find from the standard. So so what kind of new physics can you have? So just like we did for B to D star TAMU, you can write down all kinds of effective operators, and people did a lot of fits, and there are hundreds and hundreds of data that you need to fit. And what was observed that if you have a new physics in delta C9, remember the C9 operator, then you can fix it. Right? And they can come from a variety of models. You can have Z prime models left over. In the recent paper we looked at there were about 35 Z prime models that were and so many leftover models. So this is like short distance new physics. You have this, But the point is, as I said, it can also be induced by standard model of hadronic effects, and this is what we can think of. But it doesn't have to be short distance. It can also be new for fermion low mass physics. So what is the hadronic uncertainty? So the hadronic uncertainty basically comes from the fact that you can have what are these the QCD penguin type operators, where you have B2S QQ bar, and the QQ bar then forms, say, goes to a gamma and goes to B plus B minus, and or in some cases the QQ bar forms like a J psi, and then you go to B plus B minus. So that's the stuff that we had talked about before. And so we cannot calculate this. These are very messy stuff, and we don't know what to do with this. And so there was this paper by these authors who said that, this claim of new physics, that it's new physics is delta C9, you have to be careful about this. Because if I look at this kind of contribution, I can write in the most general form, and if you look at this, it looks very similar to C9, except there is a Q-square dependent factor here. Okay? Now if you say that I don't know anything about this function here, and I just calculate this and it kind of goes like Q-square, then this is a Hydronic effect which mimics new physics, mimics a delta C9. Right? And so you can generate an effective correction to C9 purely from Hydronic effects. And these Hydronic effects have been calculated by this group. So as you see here, it's a B to S, and then there is a CC bar, and it produces a gamma. This then produces N plus N minus. The problem is you can have all kinds of TCD corrections going on. So you have the blue one here, and you don't know how to calculate it. Right? So what these authors showed that even if you're away from the charm resonances, there are still these corrections which go as 1 over MC squared, and you have no idea how large these corrections are. And so you do not know what these corrections are. So how do you know it's new physics, right? And there is kind of let me kind of skip this. So you can there is instead of like the standard model diagrams, you could also have, and these were first studied by us, and then there are other people who have studied this. Instead of a charm, you could have a new state, for instance, which through loops can produce corrections like this. So in the paper we wrote, we had some effective fermion operators, and then through loops you produce Q-square dependent coupling. Anyway. But things really got interesting when they started measuring quantities like RK. So the RK was the B plus going to K plus B plus B minus K plus E minus. So you are testing for, again, in the standard model here, because the mu and the electrons are very similar in masses compared to the B mass, this is a prediction that you expect to be 1. Okay. Now here you cannot complain, you cannot explain this with Hydronic effects, because whatever Hydronic effects appear here also appear here, and they cancel. Okay. So this was a great check for all this new physics, and what they observed, and this was like 2014, was it was less than 1. So in the standard model prediction, it's supposed to be 1, it's 0.75. What is interesting, it went in the same direction as the other anomalies. If you remember, we said the branching ratio that they measured for B plus K plus B minus, B plus B minus was less than the standard model prediction. But if you didn't believe that because of Hydronic effects, now you are kind of, it goes in the same direction. It is less than 1, so it looks like this branching ratio is less than 1. And a lot of the new physics models that were, people studied to explain these anomalies now can kind of explain this RK. So the interesting thing is that the RK is something which is free of Hydronic uncertainty, and what you're seeing here is again lepton flavor viability, lepton universality viability. The standard model, you should have the same because the gate bosons couple equally to muons and electrons, but you are seeing this deviation. And in last May, there was a measurement of RK star, where instead of K, you have K star here. And again, it was less than 1, again going in the same direction. And it's again the same, and there were measurements made in 2 bins, one in the 1 to 6, and the one in the very low Q-square bin, which is okay. So now you can go ahead and include those fits in this, and now you can include the RK and RK star, and again you can look at all possible operators that you can do, and then there are about 200 data points that you fit. And now different kinds of structures emerge. So one of the solutions that emerged, remember there was the correction to delta C9. The delta C9 also is there, but now there is another solution which is delta C9 equal to minus delta C10, which is just like the standard model. Again, new physics that couples only to the left-handed part. Again, so remember when we talk about the RT star, the best fit is only new physics that couples only to left-handed objects. So this kind of gave us a hint to collect these two. So that's kind of a review of the RK and RK star. So what I'm going to do for the rest of the talk is try to kind of, talk about this connection here, and then talk about light mediators. So are there any questions or something? Or I can slow down. So here, let me, here the recent fits here. So you still have, if you fit all the data, you still get the delta C9, which is a Wilson coefficient of this. The pool is defined as the chi-square standard model minus chi-square minimum, and so there's large deviation from the standard model. And so this fit is equally good, and it gives 5.9. So this is the one that we are going to kind of look at and kind of try to connect the RT and the
So just one thing, the chi-chi, that chi-chi BS part, so the chi could be heavy, right?
No, for a Q square, we want the chi to be around the V mass.
Beam. That's a dark matter.
That's a dark matter within that. Okay, so I don't want to talk about this, but I just want to show you this diagram here. And this is a paper we did. So what we have been talking about is the new physics in this. So instead, the Z and the gamma goes into leptons. So you have, V2s leptons. But the Z in the standard model also couples to quarks, right? And so you can ask that, okay, can I see this new physics in the penguin also in hadronic decays? And you can indeed see them. The problem is that when you have the Z going to quarks, then you have to also worry about gluons going to quarks. So this is the one, this is where you're looking for the new physics, but you have to worry about all this QCD stuff as well as all the treatment stuff. So this is a lot more complicated. But it turns out that there was a puzzle, and for a long time, which is called the K-pi puzzle, and I don't need.
So just one thing, the BS to chi-chi, which you did. So did you kind of did the chi-chi to BS process? Because the Fermi is sensitive to anything B in the final state because you have photons. Like so do you?
So what we looked at was, can we see this the new physics effects in this non-leptonic decay? And let me kind of just go through and so what we have is, these are what are called B to K pi decays. So you have got a B plus going to pi plus K0. And using isospin, you can write them in this way, right? So I just want to kind of, so even without calculating this is the QCD penguin here, the tree level amplitude, and here is the new physics where we are trying to look at. So we are trying to look at new physics. Now in the standard model, this is the smallest amplitude. So you have a T and a P, and this decay also has the same T and P. Okay? Now if you neglect this, then you predict that this decay and this decay behaves exactly the same. Okay, and you predict that they should have the same CP violation. And so the puzzle was here. If you look at these two decays here, and if you look at the measurement of the CP violation, not only are they different, they're different by even the sign. So that was the long K-pi puzzle, and it's still there. And it's kind of interesting that the new physics that we are talking about in the V2S L plus L minus can kind of also explain this kind of problem. So I don't want to spend too much time on this. Let's go to combining this, trying to find a combined explanation for this RD and RT star term. Okay. And the idea is very simple. So we are using the fact that both RK and RT point to new physics which is coupling to left-hand. Okay. And so what you want to do is, right now we wrote all these operators. Now we want to make these operators invariant under the full standard model case rule. Right? And these people were trying to build this, but they were focused mostly on the RK. And what we realized is that there are only two new operators that you can write, which couple to the left-handed fields and are invariant under this the standard model. So one is the singlet, it's called the singlet, and one is the triplet. Okay, and you can kind of see here that the singlet is neutral current, and the triplet here contains both neutral current and the charge current, just like the standard model. So combination of these two operators can explain both the RD and the RD star. So that was that. And since then, many models have been built. First, this author looked at all possible ultraviolet completion of these operators, and then listed kind of models that is going to produce those operators. So there are many leptoquark models and W prime or the extra triplet vector boson models. And this recent paper is a very good paper to look at the kind of models that actually work. The basic assumption here is that what we make here is that you start with these operators, but these operators are only for the third generation. So it's new physics that only couples to the third generation. Then how do you go to the mu's and the s? So what you do is after you write this in the gauge basis, then once you go to the mass basis, then through mixing, all these new operators are generated. But everything starts with the third generation, so the new physics is in the third generation, and then through mixing, the new physics kind of feeds down into the other generations. So, but when you start looking at new models, then there are additional constraints that come from additional processes. Processes that get linked, right? So it's more useful to look at models. So, and there are many, as I said, there are 34 Z prime models and another 30 leptoquark models. So what I'm going to do is kind of just look at a very simple model, right? And that model already tells you some interesting features about it. So if you're looking for a combined explanation, then these are the things that you have to worry about. So first thing you have to do is you have to move from the gauge basis to the mass basis. And the nice thing is everything involves the left-handed field. And so we make an assumption here that this is how the down quark is going to be diagonalized. So we assume that the mixing is mostly in the second and the third generation. And once you have fixed this down type, then the CKM matrix fixes you the up type, because the CKM is just overlap of the up type and the down type. And so everything is fixed. And the same with the charged lepton. So we take the charged lepton to have something which is similar to this. So now you have kind of introduced these two new parameters, and you can look at all the constraints. So here's the simplest model. So suppose you have a new vector boson, new triplet, right? So just like the standard model, you have a mu, which would be like a W prime or a Z prime, and it couples to quarks and it couples to leptons. Now, you generate the term which is of interest to you, the operator if you remember we wrote down, is when you just integrate out the W, you're going to generate the two quarks and the two Fermi operators. But you can see that there are more to it, because you can generate 4 quark operators by squaring this, and you can generate 4 lepton operators by squaring this. So not only are you going to have B2SLL, you're going to have quark effects and pure lepton effects. So you have to kind of look at all of those things. And then things become much more constrained. So here is, for instance, the vector boson model here. And here is the constraint which is coming from RD, RD star. This is the RK. But you have to worry about the B2S mu. You have to worry about the B sub S mixing. You have to worry about all this tau to 3 mu and tau to 5 mu. And things become very, very constrained. In fact, this simple model is almost redundant. You just cannot make it. The leptoquark models, which is another UV completion of our operators, are less constrained. For instance, this is what is called a vector leptoquark, and it's a singlet, and it's called the U1, and that's the one that has received a lot of attention. So it's a vector leptoquark, And there some of the constraints don't apply. For instance, the B2S naming bar doesn't apply because the contribution is 0, and the most severe constraint comes from B sub S mixing, and that doesn't apply because the left-to-quark connects quarks to the. So things are constrained, but how can you say what are the things that, so you have all these models, so what are the searches? I mean, where do you go and look for this new states? If there's new physics, there should be new states. So one obvious thing is for collider searches, so you have TP going to TT bar plus X, because remember the new physics was mostly third generation. So if you kind of write these operators, then you can go and look for all the searches for TT bar resonances that have been done so these are from the atlas, and you get a limit around the scale of new physics to be 1.2 T. Now this is kind of an effective operator analysis. When you go to real models, this is going to break down because this is not going to work when your energy is of the order of TeV and the scale of new physics is at TeV. So what you need to do is kind of put in the more kind of models and look at the searches here. So this is again from this paper here. This is for a vector left-to-quark model, and this kind of shows you the kind of constraints that are already there and the future constraints. And this is the region which is favored by the B anomalies, and so so there's still room for things to work. So things are okay here. What about the low energy test? One of the most important tests is that you have these four lepton operators, and so like the Z prime models is going to produce tau to 3. And the present bound is 2.10 to the power minus 8. Bell expects it to reduce it to 10 to the minus 10. The reach of LSCP is somewhat weaker, 10 to the power 9. But if you look at all the constraints, the prediction is that this should be close to 10 to the power minus 8. So this, if nothing is, if this present limit is lower, then these Z prime models are extra, vector boson triplet models are highly constrained. So it's probably not going to. For the left-to-quark models, we found that upsilon decays actually produce some interesting results. And one of the decay that we found was upsilon going to be tau, so it's lepton flavor balancing. And for the vector boson, it's kind of less, but for the left-to-quark models, it can be enhanced by a factor of 2. And this is a decay that L2 should be able to measure because they can measure it 10 to the power minus 7. In fact, there is already a search for a proposed search for this decay at L2. So these are kind of the signals that you expect in general for models in which try to expect both of them. So that's pretty much it for a combined explanation. And for the rest of the talk, maybe for the 10 minutes, we'll talk about light mediator modes. And why do you want to talk about light mediator modes? If you, so what is the problem here? So remember last May there were two measurements in two bins. So one bin is Q squared from 1 to 6, the other bin is very low Q squared. The problem at very low Q squared is that at that point the photon term, which is the C7, becomes important. And remember, what is the C7? The C7 is a term which couples to the photon. And the photon couples equally to the muons and the electrons. So the photon is not going to cause any lepton universality violation. Right? So you expect that the standard model, you expect the any new physics not to affect this very low Q squared bit. Right? Now what do I mean by that? So here is a fit. Right? So here, so let me explain. So these are the measurement of RK star. This is RK and RK in this very low Q squared bit. Now in the standard model, the prediction is 1, and the black is the experimental. And let's look at the scenario 2 and 3. So these are two kind of scenarios, like different operators. and they get a good fit here, you get a good fit here, but if you see here, they cannot, in the very low Q-square bin, the effect of new physics is not much in the very low Q-square bin. Why? Because it's dominated by the C7 term, right? And the C7 term is is connected to the photon couples equally to the muons and the electrons, and so the new physics cannot compete very much with the photon term here. Okay? So all these scenarios give a very good fit to this, in this bin are 1 to 6 bin, but they don't give a good fit to this. Okay, so now there will be new measurement coming from the elasticity of this. So this is, is a problem at the present time, even though everything is, within 1.5 signals. So it's not that big. And so the question was, can we have light mediators? So all these scenarios where we have mediators, can we have a light mediator to explain this? And so we kind of started looking at light mediators even before this data came. And it turns out that it's not, there are a lot of constraints. So the first paper we wrote was before the RK-star measurement. And we were trying to understand the RK and connect it to G-2. And so without writing any model, we said, let's just write down a flavor changing couple. And it couples to a Z prime which is light. By light we mean that it's less than the muon mass, twice the muon mass. So the Z prime cannot decay to 2 muons. It doesn't couple to electrons. So there is electron university violation here. And since we are interested in the low Q-square region, so even though I don't know the form factor, I can expand this in this general form. So and I can just keep up to Q-square. So the question is, you can kind of divide this model into 2 groups. One is A, when the Z prime couples to neutrinos, and when the Z prime doesn't couple to neutrinos. Now in this paper, we're interested in also looking at the neutrino interactions, so we wanted to couple it to neutrinos. But it turns out that if we couple it to neutrinos, things get, there are problems there. So because the Z prime is light, it can on-shell decay to 2 neutrinos. So this decay, V to S nu bar, is dominated by the 2-body decay, V to S. Okay. And because it's a Z prime, there is this longitudinal polarization which is enhanced by EZ prime over NZ. Right? So EZ is the mass of the B here, and if you have a Z prime which is 100 MeV or 10 MeV, there is a huge enhancement of this. Now, there are measured constraints coming from V to K mu, and it forces this coupling to be very small, of the order of this V and Z prime coupling to be order of 10 to the power 9. Now, to explain RK, you also need, then you need the muon coupling to be order 1 if you want to explain RK. And that is a problem with, it conflicts a lot with the G minus 2 measurement. You cannot have, you need the muon coupling to Z prime to be order 10 to the power minus 3. You cannot have order 1 coupling. So, so what it says is that in this coupling, this whole scenario is only going to work if I set this term, somehow the first term is 0. Now if I take the second term here, Q square over mu square, then I will get a suppression. And this suppression just cancels the enhancement which is here. Right? And then things kind of work out. Right? So the first constraint basically rules out the case when you just have a constant term here. But if you have a Q square dependent term, then things are fine. And so now you assume that the coupling to Z prime is Q square dependent, so it's of this form. And then things are fine. And the case B is that you don't care about neutrinos, so you just say the neutrinos will not couple, so you don't care about this. So there are 2 cases you can have. One is where the flavor chain decoupling is proportional to Q squared, and the other where the flavor chain decoupling is Q squared independent. Now if you go and look at V to S L plus L minus, this is how one of the case A looks like, and this is how it looks like. And as you see that the Q square dependence is very different. Here, because if you're taking the Z prime to be less than Q squared, effectively the Q square and Q square cancels, and you have effectively like a four-form interaction, as if it is coming from a heavy new physics. Right? While here, there is a very non-trivial Q-square dependence. So you can take this to new physics amplitude and try to fit to the 200 data points, and you see what kind of fit works. And it turns out that this gives a very poor fit. It doesn't work. So this doesn't work. This works well. And so we have somehow to kind of find interaction, which has to be Q-square dependent for a light. But it turns out that this still doesn't explain this data. So it can explain all the other data, all the branching ratios, RK in this 1 to 6 bin, but when you come to this low Q-square bin, it's still away from those bins. So the last paper we kind of looked at was instead of scalars, we said instead of Z prime, let's look at scalars. And instead of coupling to only muons, let's couple it to electrons and muons and see kind of what works. It turns out that if you have scalar coupling to muon, it doesn't work, because in that case, RK and RK are increased from the standard model values, which is not good. Z prime couplings to muon didn't work, which we just showed here. So we have to invoke new physics coupling of Z prime going to electrons instead of. So the ratio is less than 1. So you can either decrease the denominator or increase the numerator, increase the denominator. So here we are kind of increasing the denominator here. And we chose the mass to be around 25 MeV because there are some branching ratio constraints. They're all measurements below 30 MeV. And there are a whole bunch of constraints coming to electrons. When we started looking at electrons, we said no way we can get things to work with electrons because there must be so many constraints. And there are many constraints for all kinds of G-2, Babar, many fixed target, big jump experiments.
So you use G-2 to electron to constraint?
Yeah, G-2.
But I thought they use that to measure alpha. G-2 electron is used to measure alpha.
It is a measure.
Yeah, so you don't use that for any constraint.
Anyway,
maybe that alpha which you can extract that's totally screwed up by this by using effect, and then it will destroy something else.
Right.
But by itself, G-2 electron.
Okay. So that's a good point. Yeah. But I don't know. This was a paper by this Seattle group, nuclear physics, Miller or something. But you can find some areas, so you see the coupling is of the order of 10 to the power minus 4. And you can make things work. And so I don't want to kind of ask you to follow this. So if you look at, so here is the pole. So it's like, you get a good pole. If you include all the data here, and these are the kind of couplings that you get. And so for the GEE combined, it's about 10 to the power minus 8. GE is about 10 to the power minus 4 or minus 3. GPS is 10 to the power minus 5. So you can make everything kind of work. But then there are other constraints you have to consider. There are these branching ratios that there's B to K plus E minus, the inclusive and something. So out of all the solutions, only a few survive. And so what we made is a prediction. Remember, there was a measurement of RK star, which was measured in the 2 bins in the, what is called the 1 to 6 of the center Q-square bin and the very low, which is here. There is no measurement of RK in this very low Q-square bin. So we have a prediction for this. And you see that a measurement of RK in the very low Q-square bin can rule out some of the cases. In some cases you have a prediction of 0.7, while in other cases it's 0. So if RK is measured in this very low Q-square bin, then we can actually tell whether we're seeing a scalar or a light vector. So generally the light scalars are predict RK to be close to 1. I think the vectors are predicted to be close to. The values of RK and RK start to put on the base. So this is a measurement hopefully LSTV will do, and will be interesting. So the point is the low Q square, the very low Q square bin is kind of interesting. Hopefully new results will come and then we'll kind of see whether this number changes or not. But if it still remains in this range, then it's something, that's a problem for model reader. So that's kind of pretty much it. I just kind of went through this things quickly. So there are several anomalies in B decays, and it's interesting because it indicates electron non-universal interaction. And these anomalies may be related, and there are some specific models that you can these models are kind of specific because they have some specific predictions. Things are okay with collider mounts. But these are electron universality violating, so you should also see electron flavor violating, like epsilon increase tau. These were the interesting modes, tau to 3 mu, like epsilon to tau. New physics, light physics is highly constrained, but it's an interesting scenario which people have started discussing recently and might have some connection to people like coherent scattering and stuff like that. It's what we are looking at here in the group here. So they will put in more constraints on this, the lightning physics. So this is the kind of thing that we are kind of interested in now to see if we can kind of make it work. So that's it. Thank you.